one of the directors at the Kavli Institute in Santa Barbara. I am going to talk to you, though, about cubes, much like some of the other speakers. This sequence is a mental gift. I hope to get to it. It doesn't completely solve a problem that Martin Gardner posed, but it goes some distance in that direction. Okay. So like I said, I'm a physicist. I'm going to talk about collaboration, which started a while ago with K. de Vicci, and even goes back to Martin Gardner in a deep way. Martin Gardner wrote in the mid-'60s a Scientific American article devoted to hypercubes. And in that article, he mentioned Peter Newland, I believe. I couldn't find a great picture of Peter Newland, so I didn't put one there. But Peter Newland had this beautiful solution to a problem which is attributed to Prince Rupert. Prince Rupert was minor royalty in the 1600s and had some technological and mathematical interests. He placed a wager, in fact. He wanted to know if you could take a cube and pass it through a unit cube, if that cube you pass through could be bigger than the unit cube, let's say. Well, you can define your units any way you want, but it turns out it can. John Wallis proved it could. John Wallis did not give the optimal solution, and that was left for Peter Newland in the 1700s, and this is his solution. It's very interesting because it has some nice rational numbers in it. If you go along the edge, that vertex of the, let me say one thing, I've now reformulated the problem, so I'm going to look for the largest square that I can fit entirely in a unit cube. Because obviously, if I drop a cube through the plane defined by that square, then it will go right through the cube. Well, that vertex of the square divides the unit side length of the embedding cube in the ratio 1 to 3, so that's 1/4 and 3/4. And from that, you can get all the other dimensions. Now, Martin Gardner mentioned this in his Scientific American article, and then he also posed a novel problem, which was, what's the largest cube you can fit inside a unit tesseract? And that question is actually very interesting. And he elicited a number of solutions. I believe there were about 6 solutions. He wrote about this a couple times. It was a problem he kept coming back to. Sometimes he didn't read his own correspondence correctly, because I went back and looked at his notes that are at the Green Library at Stanford. And in fact, he got 6 correct solutions for that cube in the hypercube problem. What I'm showing here is not the cube in the hypercube, but rather the largest square that fits into a hypercube. And this is a further generalization of the problem. So instead of asking what the side length of the largest n cube you can fit in an n+1 cube, you could ask what's the side length of the largest m cube you can fit inside of an n cube. And that generalization is quite beautiful. It has all kinds of symmetries and special properties. So for instance, one is displayed here. If m divides n, then that side length is the square root of n divided by m. And that agrees with all the special cases you can think of. So in the special case that m divides n, then this side length is equal to the square root of n over m. And there's lots of other nice properties that I could mention, but I don't have time. So to tackle the full problem, I got together with another mathematician, a mathematician named Terry Ligocki, and we just decided we're going to solve this problem numerically. So we used a physics technique called simulated annealing. It's based on statistical mechanics and has the Boltzmann factor built into it. But the basic idea is that you start a computational problem at a high temperature. It's not a real temperature, it's a computational temperature. And then you have an annealing schedule. An annealing schedule just means you have some scheme for lowering that temperature as the computation proceeds. And what we found was that we could solve this problem numerically by making little Monte Carlo moves on the embedded cube. The little moves just rotate it in different angles and change its scale slightly until you get to the optimal solution. So here's a plot. I mislabeled the y-axis. This is a plot of 1 over the side length versus the ratio of m over n. That ratio turns out to control the whole problem. At least that's our conjecture. There's one step we're missing. We don't have a proof for this fact, but the statement is that if you can factor out in the dimensions of space a common factor in m and n, then you've reduced the problem to the factored problem. If that's true, then this ratio controls the whole problem. And what I meant to plot here was actually 1 over the square, because the square has these nice properties. As I mentioned, this ratio, square root n over m, every time they're commensurate, you come back to that. So if you take 1 over that, you're just plotting then m over n versus m over n, which would be the diagonal. So all of those points, when I plot the square, would just, all those points where it's 1 over an integer would just lie on the main diagonal of that plot. This is another view of the same information. So call these kind of lobes. So this is a fractal plot, actually. So there's a fractal hiding inside of this problem. If you look at the values of n over m that are between 1 and 2, between 2 and 3, between 3 and 4, and so on, then I can take that data and replot it. Again, I've scaled the y-axis in a funny way. I've taken 1 over the side length squared, and I've subtracted out something. But that's not important. That's just to take into account that diagonal. You see, each of those lobes has a kind of self-similar structure, except you have to rescale it by another factor. OK, I want to now end by going back to Gardner's original question. That was the special case where you looked at the n, well, let's call it the m cube embedded in the m plus 1 cube. What are the side lengths there? So I made a little table of some of the numerical results just to show you the funny pattern. So what's the biggest line segment you can fit in a unit square? Well, it's the main diagonal, so that has a length of square root of 2. So I put that as the first entry, and then I've squared it just to show what the square looks like. The next value was Peter Newland's value of the square root of 9 over 8. That's what you get with that funny 1/4, 3/4 construction. That squared is obviously 9 over 8. The next value was proven by Vicci to be the correct value. That's for the cube in the 4 cube. That was Gardner's original question. And then the rest are numerics. And I have numerics now going up to hundreds of dimensions for this problem. Now, what's remarkable is that there's a regularity to this which is striking and involves the number 9. And I could explain in more detail why it's 9, but I'm not going to do it right now. If I were to write those squared lengths as a continued fraction, or just the beginning of or an Egyptian fraction, if you like, an Egyptian expansion, then I would get for 2, 1 plus 1 over 1. For 9/8, 1 plus 1 over 8, and so on. Those are the integers I put here. Of course, after the second row, it's not exact. That's just an approximation. but you can already see these numbers are increasing geometrically. It turns out asymptotically they increase with a factor 9. And there's a prefactor there, which is very interesting. I have it out to hundreds of digits now, but I only put a few here. So now I've inverted it. The remainder, if I were to write the solution to Gardner's problem is 1 plus a small amount, then that small amount looks like some constant times 1 over 9 to the power of the hypercube. That is the dimension to the power, which is the dimension of the hypercube. And that constant, I have no idea what it is. So I'll leave that as another mystery that Martin Gardner kind of implied in his early work. Thank you.
Thank you, Greg.